Today we're going to be proving a neat little theorem about the Fibonacci sequence that's not totally obvious. But just as a refresher, what the Fibonacci sequence is it's defined like this. The 0th term of the sequence is defined to be 0. The first term of the sequence is defined to be 1. And then to find the other terms of the sequence, you just add the previous two terms. So for example, if you want to find f of 2, this guy right here, well, you just do 0 plus 1 and you get 1. Okay, like if you want to find f3, this guy, well, you do f1 plus f2, 1 plus 1, that's 2. And keep going, et cetera, et cetera. If you want to find f11, well, you do f9 plus f10, which you presumably would have previously calculated, 34 plus 55, and yes, that is 89. By the way, it should be noted that some people have their sequence start at 1 instead of 0, so they have f1 be the initial term of the sequence. However, I'm going to start at f0 for the sake of generality. This sequence has a ton of cool properties, but here's one of them that you probably didn't know about. If you add up the first so many terms of the sequence, it's always going to be one less than the term that appears two ahead. So like if we add all these numbers, 0 plus 1 plus 1 plus 2 plus 3 plus 5 plus 8, what do we get? That's 2 plus 4 plus 3 is 7 plus 5 is 12 plus 8, that's 20. So this comes out to be 20. And look, 20 is one less than 21. And so this always works. What this theorem here is saying that is if you add up all the fi's from f0 all the way to fn, you get fn plus 2 minus 1. So in this example, if you do add up f0 plus f1 plus dot, 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 all the way to f6, you get f8 minus 1. But why is this theorem true? Let's try to prove it. Let Pn be the proposition that this is true. Prove that this is true for all n. What we got to do is two things. One, we got to prove that it's true when n is 0. And then two, we got to prove that P of n implies P of n plus 1. In other words, whenever this formula is true for some random n, it's also true when you substitute this n with n plus 1 instead. So first, let's prove P of 0. This is called our base case. Well, if you plug in 0 for n, what do you get? Well, you just get I goes from 0 to 0 of fi. What is this equal to? Well, adding all the fi's from I equals 0 all the way to 0. Well, this is just f0, right? And what's f0? It's 0, right? It's the 0th term of our sequence, this one right here. So this just comes out to be 0. Okay. But now what about this guy? Well, this comes out to be f of 0 plus 2 minus 1, which is okay. F of 0 plus 2, that's just so we get f2 minus 1. Now what's f of 2? Well, it's just this guy, 1. So you get 1 minus 1. And hey, look, it's 0. So these are both equal to 0. So that means these guys are the same. So we see that P of 0 has to be true. Next is our inductive step. We want to show that whenever P of n is true, P of n plus 1 also has to be true. So we want to assume that P of n is true for some fixed arbitrary integer which is greater than or equal to 0. Now, what does P of n being true mean? This is just saying that this is true. We can copy paste that. And what do we want to show? We want to show that P of n plus 1 is true as well. In other words, we want to show that this equality is true. If we can do that, we're done with the proof. So how do we do it? Well, we can rewrite this by simplifying. If you add all the terms from 0 to n plus 1, that's the same as first adding all the terms from 0 to n, and then adding the n plus first term, right? Then also this guy we can simplify. F of n plus 1 plus 2, that's just the same as f of n plus 3, okay? All right, but now here's the thing. We're assuming that this sum right here is equal to this, right? So we can substitute. So this is the same as saying that we want to show that this guy plus f of n plus 1 equals f of n plus 3 minus 1. And now if you do a little bit of algebra, you can add 1 to both sides of the equation to get rid of this -1. So we want to show that f of n plus 2 plus f of n plus 1 equals f of n plus 3. But guess what? We know this is true. Why? Because to get a term in the Fibonacci sequence, all you got to do is add the previous two terms, right? So therefore, this equality holds. So we showed that whenever P of n is true, P of n plus 1 also has to be true. And therefore, by the principle of induction, we're done. So this equality holds for all positive integers n.